Let's understand the hypothesis testing with an example. We have a question here. Is the shock avoidance response of 50 rats, sample size is 50, treated with some specific dose of a new compound greater than the known mean, and the mean over there was 60. We got the sample mean y bar equal to 62, and our standard deviation which we get was equal to 9. Let's formulate the hypothesis. So here we are looking for some mean greater than some known mean or mean under the null. So mu is greater than mu naught. Remember, in hypothesis testing, we will always use Greek letters, parameters here, because we are using the sample mean to talk about the population mean itself. So inference is about the population. So always in both hypothesis, null and alternative, we will use those parameters, Greek letters. So mu is greater than mu naught, whereas under the null, it's less than or equal to, that is the total negation of it or reverse of it. We are looking for some mean greater than 60, that was the mean under the null, and h naught would be mu is less than equal to 60. So that is a one tail towards right. So our alpha will be in the right tail of this curve or null curve. Mean under the null is 60. We will draw this curve. We said the sample size. Sample size is already given, so it was 50 in this case, and alpha was 0.05. Most commonly we use 0.05. Sometimes we also use 0.01. So in this rats example, we'll choose alpha at 0.05, and we will assume that we have the resources to work with 50 rats, so n is equal to 50. Statistical test, standard is 30, it's large sample, 50 is large sample, so we will go and do a z-test. We determine the rejection region or critical region, so alpha is towards right. This is the null curve centered around the mean under the null, which was 60 in this case. So our rejection region is towards its right, top 5%. We will go onto this curve and this table and see where this 0.05 top 0.05 or top 5% lies. If you go from the bottom, since the table comes from the bottom or from the left, so we will look into the value in the table, that is 0.95. So it's not given there, but the values which we get in the table is 0.945, 0.9495 and 0.9505. Our value is in between them, so we take their average. The number here is 1.6, and the other digit we pick this one, that is 4, and this one, that is 5. So it is in between these two, so we might take the average, or we can round off to 1.65 as. So it is 1.645. We can also get it from Excel. Nest inverse point 0.95. We plug in because we are looking for the right tail. If you plug 0.05, it will give you the value that's left. It will be the same number with an opposite sign, that is a negative sign. All right. So that means this 0.05 on this side and 0.95 on this side, since it comes from left. So 0.95 and 0.05, that is your top 5% of the area. So in order to reject the null hypothesis, your observation should be here in this region. Its p-value should be greater than 0.95 or if you come on this side, and if you go on this side, it should be less than 0.05 or your alpha. If you talk about the actual number, we can also get it through Excel or through our calculations. So actual number should be some number greater than 62.1. So 62.1 is the number that separates the lower 95% to the upper 5% of the curve. We gather data and we do the test statistics so that we get it, the number we get it, we calculate it, our test statistics is 1.57. It will be y bar, mean under the null, 62 minus 60 divided by standard deviation divided by square root of n. So that thing is your sigma y bar, our standard error, which is 1.273. 2 divided by 1.273 is 1.57. So that's your z calculated. It's one tail test towards right, and this is a critical region, so you should have a number bigger than 1.645. The number we get was 1.57 here. See where it falls on the curve. So it's in terms of numbers, this critical number should be 62.1. Our number should be greater than this in order to reject the null hypothesis, whereas the number falls here, that's 62. And the calculated is 1.57. So we do not have a big number here, and our z calculated is less than z critical. We fail to reject. We can also calculate from Excel. The function is norm.dist. We plug in the number here, we plug in the mean under the null. This is a sample mean obviously, and this is the mean under the null, 60. And in this argument where Excel is looking for standard deviation, now we are not plugging in the standard deviation, rather we are plugging in the standard error here, this number. And the probability from the left which we get over here is 0.9418, and towards right it is 1 minus 0.9418. Decision, either we're gonna reject or fail to reject. So we know that we reject for a one-tail test towards right if z calculated is particular alpha or z critical. For a left-tail test, z calculated should have been smaller than the z at that particular alpha or z critical. And normally towards left-hand side, it gives us a negative number. For a two-tail test, we should have rejected if our absolute value of z calculated is split into two, right and left. Our z calculated is 1.57, so that does not exceed our z critical value of 1.645. So we fail to reject the number, and we conclude that at alpha equal to 0.05, I fail to reject the null hypothesis. I conclude that I do not have sufficient evidence to say that the population mean is n. It was a one sample test of means, and we were dealing with large samples. Let's see the other scenarios. The p-value for this particular z, which was our calculated z, 1.57, is from left it is 0.9417, and since it's a right tail, so we are looking for some z greater than this z. Probably seeing the z greater than 1.57, that is, it will be given by 1 minus 0.9417, which is equal to 0.058 to reject the null hypothesis. So here it is greater than that, so that's we fail to reject. You can calculate 10. Our number is 62. Again, less than that, so we fail to reject. In all scenarios, here we fail to reject the null hypothesis. Let's look into this table, which is very interesting. So if our null hypothesis is correct and we reject it, then this scenario is where we are seeing some false positives. So here we have on this side we have the null hypothesis, so it may be correct or it may be wrong, and then our decision, either we null hypothesis or we fail to reject the null hypothesis. So two possibilities on both sides. we get the 4 combinations. So if we reject the null hypothesis, which was actually correct, we call it type 1 error or alpha. We also call it false positive. False positive. So if our alpha is 0.05, that is the probability of type 1 error. We have the probability of false positives that is equal to 5%. So if we do 100 tests, we can expect to have 5 tests as false positives. Suppose we reject the null hypothesis and that was actually wrong. So in this scenario, we call it as true positive. That is what is most wanted. So we should have true positives. Right? So getting true positive is your power, statistical power. If we reject the null hypothesis, if we fail to reject the null hypothesis and that null hypothesis was actually correct and we fail to reject it, so that is the true negative, true negative. So that is, if this is alpha, it is 1 minus alpha. Beta is type 2 error. That is, there was the null hypothesis was wrong, but we failed to reject that. So we were not able to reject a null hypothesis that was wrong. So that's our type 2 error or beta. So that's our weakness. What is our power then? Power is 1 minus beta, 1 minus the weakness. So power is power to reject. Tests of hypothesis are evaluated by computing the probability that test rejects false the null hypothesis. This is called the power of the test. Power is 1 minus beta. It's power to reject.